Ever wonder what really makes our devices tick? Well, today, we're diving deep into the heart of electricity. We're going to tackle potential difference in this thing called electromotive force, or EMF, to uncover the secret that's happening inside every single battery. Let's get into it.
You've seen it a million times, right? That 9V printed on the side of a battery? But if you ever stop to think about what that number actually means, is that the whole story? Well, as it turns out, there's a little bit more going on inside a real-world battery than you might expect.
So here's our game plan. We'll start with the basics. What even is potential difference? Then we'll introduce its big brother, EMF. We'll uncover the secret of real batteries, use what we've learned to solve some problems, point out a few common mistakes to avoid, and then we'll see how all this physics powers the world right there in your pocket. All right, first things first, we have to build our foundation. To get anywhere else, we need a really solid grip on potential difference. You probably know it by its more common name, voltage. This is square one for pretty much everything in an electric circuit. So what exactly is voltage? Let's just forget the textbook definitions for a second. Think of it like this. Voltage is all about energy. Specifically, it's how much energy each little packet of charge, each coulomb, is carrying with it. It's not the flow itself, that's current. It's the oomph per charge. A higher voltage just means each little charge is carrying more energy to do work, like lighting up a bulb. And this whole idea gets captured in a super simple formula. V equals W over Q. All it's saying is that the voltage, V, is just the energy transfer W, which we measure in joules, divided by the amount of charge, Q, in coulombs. It's a really direct relationship. You pack more energy into each charge, you get a higher voltage. That's it. Okay, so voltage is the energy that charges use. But where did they get that energy in the first place? That's the big question. And the answer leads us to the source, the engine of the whole circuit, which has a fancy name, electromotive force, or EMF for short. Now, I gotta warn you, the name electromotive force is kind of misleading, because it's not a force at all. It's actually a measure of energy per charge, just like voltage. But here's the key difference. EMF is the total energy the battery gives to each charge. It's the perfect, ideal, maximum voltage that battery could ever produce, like when it's just sitting on the shelf, not connected to anything. So let's nail this down, because it's important. EMF is the cause. It's the total energy the battery supplies. Potential difference, which we often call terminal voltage, is the effect. It's the actual energy that's available to be used by the stuff in your circuit. Here's an analogy. Think of EMF as your gross salary, and potential difference is your take-home pay. There's always a little bit lost along the way. So where does that tax go? What's the deal with that missing energy? Well, that brings us to the little secret hidden inside every single real-world battery, a concept called internal resistance. You know, nothing's perfect, right? And that goes for batteries too. The chemicals and metals and all the stuff inside a battery aren't perfect conductors. They actually resist the flow of charge just a little bit. And this opposition, happening inside the battery itself, is what we call internal resistance. We use a lowercase r for it. To help us picture this, physicists model a real battery as two parts combined. First, you have a perfect, ideal source of EMF, and right next to it, in series, is a tiny little resistor R. And both of these are packaged up inside the battery casing. So before a charge can even get out into the circuit, it has to fight its way through this internal resistance first. And here's why that's such a big deal. As soon as you connect something and current starts to flow, those charges have to push through the battery's own internal gunk. And pushing through takes energy. That energy gets wasted, usually as heat, and it creates a small voltage drop inside the battery. We call these the lost volts, and they're equal to the current I times the internal resistance R. So the voltage that actually gets out of the terminals is the original EMF minus those lost volts.
And this all boils down to the master equation for any real battery. The EMF equals the terminal voltage V plus the lost volts, which is I times R. Really, this is just a statement about energy conservation. The total energy given to a charge gets split into two jobs. One part does useful work in the circuit, and the other part is used up just overcoming the battery's own internal resistance.
Okay, theory is great, but the best way to really understand how all these pieces fit together is to actually use them. So let's roll up our sleeves and walk through a couple of classic physics problems to see this stuff in action.
Let's start with a really fundamental one. We're told how much work is done and how much charge is moved. We need to find the potential difference. This is a straight-up test of that very first definition of voltage we talked about. All right, we grab our formula, V equals W over Q. We just plug in the numbers they gave us, 30 joules of work divided by 2 coulombs of charge, and that gives us an answer of 15 joules per coulomb, which of course is just 15 volts. Easy peasy. Okay, now for a problem that's a bit more like the real world. We've got a battery with a known EMF, its ideal voltage, and some internal resistance. We connect it to a resistor. The question is, what's the actual voltage we can measure across the battery's terminals while it's running? Now, what's really cool here is we can solve this 2 different ways, and we should get the same answer. First, let's find the total current in the circuit. Current is the total voltage, which is the EMF, divided by the total resistance, and that's the external resistor plus the internal one. So that's 12 volts divided by a total of 6 ohms, which gives us 2 amps. Now we can find the terminal voltage by just looking at the external resistor using Ohm's law, V equals IR. So 2 amps times 5.5 ohms, that's 11 volts. But check this out. We can also use our new formula, V equals EMF minus the lost volts. That's 12 volts minus 2 amps times 0.5 ohms, which is 12 minus 1, and that also gives us 11 volts. So that 12-volt battery is only actually providing 11 volts to the circuit. The other volt is lost inside the battery itself.
Okay, getting these problems right is key, but it's also really easy to fall into a few common traps. So let's quickly go over some of these pitfalls to make sure you don't make these same mistakes.
The biggest one, number 1 with a bullet, is mixing up EMF and terminal voltage. Just remember, EMF is the ideal total, terminal voltage is the real-world result. Second, people always forget to add the internal resistance when they calculate the total resistance of the circuit. Don't forget, it's part of the path the current has to take. And of course, the classics, always check your units, joules, coulombs, volts, amps, ohms. And finally, don't mix up current, which is the flow, with charge, which is the actual stuff that's flowing. Now, this isn't just some abstract physics for an exam. These concepts explain how the technology you use every single day actually works. Let's connect the dots to the real world.
Have you ever noticed your car's headlights dim just for a second when you turn the key? That's internal resistance right there. The starter motor pulls a massive current, which causes a huge lost volts drop inside the battery, and the terminal voltage available for the lights dips for a moment. Or how about an old phone that just dies when it says it has 20% battery left? As batteries age, their internal resistance goes up. This means more energy is lost as heat inside. The terminal voltage drops like a rock, and the phone shuts down to protect itself. All right, time for a quick quiz to make sure these ideas are locked in. Question 1. When is the terminal voltage of a battery exactly equal to its EMF? It's when no current is flowing. If I is 0, the whole IR term for lost volts becomes 0. Okay, next up. If you increase the external resistance in a circuit, what happens to the terminal voltage? It actually goes up. A bigger resistor means less current is flowing, which means fewer lost volts. So the terminal voltage gets closer to the ideal EMF. And last one, what form of energy do those lost volts turn into? They become thermal energy. In other words, heat.
And that brings us to our final thought, that energy, those lost volts that get turned into heat inside the battery, that's not just some number in an equation. It's the very reason your phone gets warm when you're charging it, or your laptop heats up when you're gaming. It's the price of reality. It's the little energy tax that internal resistance takes every time. It's physics, happening right in the palm of your hand. Thanks for tuning in.